Alright, so this is a continuation of the 4.5 integration by substitution video. This is part 2 where I'll just be discussing U substitutions with definite integration and integration of even and odd functions. So yeah, here I have, if the composite function u of g of x has a continuous derivative on the closed interval a to b, and f is continuous on the range g, then the integral of f of g of x times g prime of x dx equals the integral from g of a to g of b of f of u du. It's pretty wordy right there. It's a lot simpler than that. It's pretty much doing the exact same thing as integration by substitution in the last video, except this time when you remember that when you solved for definite integration in I believe it was 4.3 or 4.4 with the fundamental theorem of calculus, what you would do is you would just use the limits that they tell you on the within the problem to as what you're going to plug into your integral equation. And in this case, when you're using a u substitution, you can do this method again, but it's a lot more work than I'll be showing in this video. So pretty much what the new idea is that you're going to have to evaluate for these endpoints at your u equation. So pretty much whatever they give you in the original problem to go from some value to some value, you're going to plug these values in to your u equation, and you're going to get some new values that you're going to set as your limits. This will make more sense with the example. So here we want to take the integral from 0 to 1 of x times x squared plus 1 to the third dx. First thing we'll just do our basic u substitution integration, and this time we just won't have the plus c. So for this one, we'll make our u x squared plus 1, take the derivative, and that's 2x. Bring our dx over to the other side, and we have an x dx, but we don't want this 2, so we're going to divide by 2 on both sides. And so now we have I'm going to split this part up into 1/2 du, just so I can put the 1/2 out in front. And so we've got 1/2 u to the third du. And now we've got to, instead of just bringing down 0 and 1 and putting them in this spot right here, because we're now solving in terms of u, we've got to change our limits to our restraints in terms of u as well. So in order to do that, we're going to solve u for 1 to get our upper limit, and u for 0 to get our lower limit. Now, when I plug 1 into my u equation, I'll get 1 squared plus 1, and that equals 2. So this 2 is going to take the place of the 1, so it's going to be right there. Now we're going to do the same thing with 0. 0 squared plus 1 equals 1. We're going to plug in this 1 and replace the 0, or we are going to replace the 0 with the 1. So the 1 is going to go right there. Now you just solve this just like you would using fundamental theorem of calculus. You have 1/2, do our integration, so u to the 4th over 4. Now from 1 to 2, so 1/2 times 2 to the 4th over 4 minus 1 to the 4th over 4. Simplify all that, and you should get 15/8. And so that's your definite integral of this equation. My next example involves just a little bit of trig. And so if we look at this, first thing we're going to do is just look, okay, since we have a function inside a function, we're going to need to make a u substitution. So u, we'll set it to 2x over 3. Take the derivative, and you get 2/3. Bring your dx to the other side. You can multiply both sides by 3, so you get 3 du equals 2 dx. All we can get on this side is just dx, so we're going to have to divide by 2. So here's our u substitution. So cosine of u, and I'm actually going to split this up to 3/2. 3/2 times du, because remember that you can bring these constants out into the front of your entire integral. And now instead of using 0 to pi over 2, we're going to have to rewrite these limits in terms of u. So u of pi over 2 equals 2 times pi over 2 all over 3, which equals pi over 3. And then u of 0 equals 2 times 0 over 3, which equals 0. So our new limits are from 0 to pi over 3. And now we are just going to do our basic integration once again. 3/2. The integral of cosine u du is sine of u. And we're now going from 0 to pi over 3. 3/2 times sine of pi over 3 minus sine of 0. And that should give you 3 root, after some simplifying, 3 root 3 over 4. And there's your integral. Now this next thing, it's more of a concept idea. Integration of even and odd functions. It's just some ideas that can be handy if you're asked to solve for something that goes from some negative to some positive value, and they tell you that the function's even or odd or something, or using the evenness or oddness of the function determine what the integral is. But let f be integrable on a closed interval -a to a. If f is an even function, then the integral from -a to a of f of x dx equals 2 times the integral from 0 to a of f of x dx. For a picture, first of all, just recall that even functions are when opposite input produces the same output. So f of x equals f of x equals f of negative x. So in this case, if f is an even function, here I have a picture of a cosine graph, which is an even function. Then the integral from -a to a of f of x dx, so that means that it's saying the integral of this area right here is going to be equal to 2 times the area from 0 to a. So it's saying that it's equal to 2 times the area of this section right here. And if you look at the picture, then that makes sense, because remember that even functions are symmetrical across the y-axis, which means that on one side of the y-axis is going to be the exact same on the other side of the y-axis. So if you've got an area of 2 over here up to a, then if it's symmetrical across the y-axis, then the integral will be 2 as well from 0 to -a. Hopefully that makes sense. The second one is if f is an odd function, then the integral from -a to a of f of x dx equals 0. For an odd function, recall that f of x equals -f of x. They're symmetrical across they're symmetrical around the origin. So if you look at my picture here I have a sine graph. Sine is an odd function, and so it's saying the integral from there to there equals 0. If you think about it, since it's symmetrical around the origin, then that means when there's some sort of positive value, as you can see here, then there's going to be an equal value, but an opposite equal value. So like here you can see you've got this upward like hill with a positive integral underneath it, but on the left side you've got the same size of the hill in the negative direction, which produces a negative integral. And so essentially the two things cancel out because this one's positive and this one's negative, so that means that the integral will just be 0.